Okay, class 12, the topic that we are going to discuss today in this video is the capacitance of a capacitor with, of course, a parallel plate capacitor with a dielectric slab of thickness T in between the two plates, where the thickness T of the dielectric substance is lesser than small d, where d is the separation between the two plates. Okay, so what we basically have is we have a parallel plate capacitor, and in between the two plates of the capacitor we have filled, or we have inserted a dielectric substance having thickness T. Only thing is, the thickness T of the dielectric substance is lesser than the separation between the two plates. So to say, the dielectric substance is not completely filling up the space. It is not completely filling up the space between the two plates. All right. Okay, so this is the case that we are going to discuss today. All right, but before we discuss that, let us do a recap. Okay, remember, if we have, going back to Gauss's theorem, okay, if we have a positively charged plate and a negatively charged plate, the separation between them being filled up with free space or air. Okay, so we had seen that the electric field at any point in between the two plates, at a point here, at a point here, anywhere in between the two plates, the electric field in between the two plates will be given by sigma by epsilon naught, where sigma is the surface charge density and epsilon naught is the permittivity of free space, that is the permittivity of the medium that is in between the two plates. Okay, so remember, following this, if we have two plates, one positively charged, one negatively charged, and the separation between the two plates, say for example, is completely filled up. Okay, is filled up by some substance, having permittivity epsilon. All right, is filled up by some substance having permittivity epsilon. It need not be, the space between the two plates need not be completely filled up by the substance. Okay, it could be a scenario like this. It could be a scenario like this, where the space between the two plates is not completely filled up by substance. So here it could be free space in between these gaps over here. It's free space, air, and you have some other substance, some other material over here having permittivity epsilon. Don't forget what is the relation between permittivity and dielectric constant, or something called relative permittivity. Relative permittivity epsilon r is the permittivity of the medium divided by the permittivity of free space. Don't forget this relation. Okay, so any substance having a permittivity, we can also calculate its dielectric constant or relative permittivity, which is given by epsilon naught. So if this is the scenario, like, let us discuss this scenario here. If this is the scenario, like, if the separation between the two plates is completely filled up by some other medium, okay, then, like in this case, the electric field at any point in this material or in between the two plates now will be given by, let us call that E dash, it is given by sigma by epsilon, that is the permittivity of that particular medium. Remember that. If it is free space in between the two plates, the electric field at any point in between the two plates will be given by sigma by epsilon naught. If it is some material having permittivity epsilon, then the electric field intensity in between the two plates will be given by sigma by epsilon. Keep this thing in mind. Okay, so keeping this thing in mind, let us come back to our topic, all right, which is the capacitance of a capacitor with a dielectric slab of thickness T in between the two plates. All right, mind you, like I've already shown, the thickness T of the dielectric substance of this material is lesser than the separation between the two plates. Okay, so A, remember, is the area of the plates, D is the separation between the two plates, T is the thickness of the dielectric substance. All right, so keeping this in mind, the potential difference between the two plates, of the capacitor is now given by, is a sum of, if this potential difference between the two plates is V, then V is V naught plus, I've written VD over here, let me see, V dash. Okay, so V is V naught plus V dash, where V naught is the potential in free space over here. So you have free space, okay, you have free space, and you have this dielectric slab. So V0 is the potential in the free space region over here, okay, and V dash is the potential in the dielectric region over here. All right, okay, V dash you can say is the potential at any point in the dielectric substance, and V0 is the potential in free space. So the potential difference between the two plates is V0 plus V dash, or V is equal to E0 is the electric field in free space, okay, is the electric field in free space. So E0 into D minus T. Now what is this D minus T? D minus T is this free space region plus this free space region, that is the thickness. D minus T is the thickness of the free space, okay, since the separation between the two places is D, the thickness of the dielectric slab is T, so therefore the thickness of the free space has to be D minus T, okay, because mind you, again, electric field is the gradient of the potential, so therefore the potential difference will be E multiplied by distance, okay. So therefore the potential in free space V0 will be E0, that is the electric field in free space, multiplied by the thickness of free space, plus V dash. V dash is the electric field in the dielectric substance, so it is E dash into T, okay, where T is the thickness of the dielectric substance. All right, so remember, potential difference is E0 into D minus T plus E dash into T, or V is equal to, now what is E0? E0 is sigma by epsilon naught. Again, remember, at any point in between the two plates, if it is free space in between the two plates, at any point, wherever, okay, wherever in between the two plates, at any point in free space, the electric field is given by sigma by epsilon naught. All right, so the same thing is true over here. Since this is free space in between the two plates, this free space in between the two plates, the electric field anywhere in free space in between the two plates is given by sigma by epsilon naught. So E0 is sigma by epsilon naught into D minus T, plus E dash will be sigma by, I've written epsilon r into epsilon naught over here, because, or I could have, this very thing I could have written, V is sigma by epsilon naught into D minus T plus sigma by epsilon into T, where E dash is sigma by epsilon, okay. The electric field in the dielectric is sigma by epsilon, okay. Now instead of epsilon, since epsilon r, the dielectric constant, or also called relative permittivity, is epsilon by epsilon naught, so instead of epsilon, this implies epsilon is epsilon r into epsilon naught, okay. So instead of this epsilon, what I've written is here, okay, sigma by epsilon r into epsilon naught into T, okay, thereby giving me V is, I'm taking sigma by epsilon naught common from these two terms, so sigma by epsilon naught inside the bracket, what I get is D minus T plus T by epsilon r, okay. In your book you might see the dielectric constant or relative permittivity to be denoted by a capital K. All right, so this is the potential difference between the two plates of the capacitor when you have a dielectric slab of thickness T, which is lesser than D, placed between the two plates. This is the potential difference, okay. This is the potential difference. Now basically what we want to find is, we want to find the capacitance of this capacitor. We want to find the capacitance in this scenario. So what is the capacitance of the capacitor? The capacitance of the capacitor, since C is Q by V, all right, the capacitance of the capacitor will be the charge on the two plates. If the charge that we've given to this plate is Q, you have minus Q over here. Of course, this plate is connected to the ground, connected to the earth. All right, so you have plus Q over here, you have minus Q over here. All right, so the capacitance of the capacitor will be Q by V, which is Q by this expression. So Q by sigma by epsilon naught into D minus T plus T by epsilon r. Okay, all right. Now sigma again is surface charge density, which is the charge divided by the area, don't forget. All right, so let me write it over here. So capacitance is q by, let me rewrite it, sigma by epsilon naught into d minus t plus t by epsilon r. So this is my expression, okay? Or this can be written as C is q by a epsilon naught, because sigma, mind you, is charge by area. So d minus t plus t by epsilon r. So q, they divide each other out. So therefore, rearranging, what I get is C is epsilon naught a divided by d minus t plus t by epsilon r. This is epsilon. So this is the expression for the capacitance of a capacitor when the space between the two plates is filled up by a dielectric. But mind you, the dielectric is not completely filling up the space. Okay, so case 1, different cases we are going to discuss. So case 1, when T is equal to D, that is, the thickness of the dielectric is equal to the separation between the two plates. Okay, or in other words, when T is equal to D, the dielectric substance is completely filling up the space between the two plates. Okay, so when T is equal to D, what do we get from this expression? When T is D, okay, D minus D becomes 0 plus D upon epsilon r. So C becomes epsilon naught of so C is epsilon naught a divided by D minus D plus T, plus D by epsilon r. Since T is D, T and D are the same. So dd, they cancel each other out. So therefore C becomes epsilon naught a upon D by epsilon r. It's like I'm spoon feeding you all. So this epsilon r, it goes to the numerator. So this becomes epsilon naught epsilon r a by d. So this is the expression for the capacitance of a capacitor when the space between the two plates is completely filled up by a dielectric material, remember. Okay, when it doesn't fill up completely, it's this. When it fills up completely, it's this. All right, so I want to remind you of the air capacitor. In case of the air capacitor, parallel plate air capacitor, the expression was epsilon naught a by d. Okay, and when the space between the two plates is completely filled up by a dielectric substance, what is happening is the capacitance is epsilon r epsilon naught a by d. I'm rewriting the very same expression this way. Okay, so what is happening? This is for the air capacitor. This is for the air capacitor, whatever the spelling. Okay, this is for when the space between the two plates is completely filled up by a dielectric. Okay, so what happens is that when you fill the space between the two plates completely by a dielectric, the capacitance of that capacitor increases by a value, epsilon r, increases by a value which is equal to the dielectric constant of that material. Remember that. Okay, all right. So this is case 1, that is when T is equal to D. Okay, now from this very expression, we can get the expression for the air capacitor also. We can get the expression for the air capacitor. That is when T is equal to 0. That is case number 2. Okay, case number 2, I'm writing it over here. Hope you all understand. When T is equal to 0. Okay, when the dielectric substance is not there, T is equal to 0 means. That is, this is in case of an air capacitor. When T is 0, what do you get? So T upon epsilon r becomes 0. Okay, so this is 0. So what is capacitance? This becomes epsilon naught a by d. This is the expression for the air capacitor. Okay, so to check this derivation is very, very important. Okay, that is capacitance of a capacitor with a dielectric slab of thickness t lesser than d. Okay, to land up at this expression. Okay, it's important for you all, remember. All right, this much for now. Thank you.